Good morning, students. Last day we discussed differential pulse code modulation. Possibly you remember the schematic diagram. And at the conclusion, we found that if we use a predictor, then differential pulse code modulation can give comparable performance in terms of signal to noise ratio at half the sampling rate of normal pulse code modulation. Half the sampling rate means our electronics will be cheaper. Of course, nowadays in a system, the cost of the electronics is really not a matter, but the saves half of the bandwidth. Next lesson, we shall use the next technique that is called linear delta modulation. Although it is linear delta modulation, but normally when we abbreviate, we say DM. We do not normally call it LDM, we call it DM, delta modulation. And when somebody says delta modulation, you should take it as a linear delta modulation. There is another kind of delta modulation, adaptive delta modulation. In that case, the adaptive word is always used. If adaptive word is not there, you should take it as a linear delta modulation. Now, what is delta modulation? In the coder only finds whether the present signal value MT is more or less than the last accumulated value M dashed. That means, say this blue dotted line is the signal. The coder only determines the present signal value is less than the earlier signal value or more than the earlier signal value. Accordingly, it creates a 0 or 1. Now, if you do that, then what happens? Instead of 8-bit or 4-bit, you have to transmit only 1 bit. That is a tremendous savings on the bandwidth requirement. That is why that is the plus point of linear delta modulation. But you may ask that why don't we then use other modulations? We should use linear delta modulation. Always not so. As I said, every technique has some positive side and negative side. We shall discuss that. Now, this is a signal input to a comparator. Negative input of the comparator is the last signal value, and it only determines the difference. It is higher or lower, right? Then there is a sample and hold circuit. See, if it finds, say, this is the last signal value, and it is held here. That is why it is a flat top, looks like a flat top pulse. Then it finds the second sample is also higher. Then it takes one step higher and holds it there. Then it finds third sample is also higher than the last sample. Then it takes one step higher and hold there. Similarly, as long as it finds that the present sample is more than the last sample, it goes on increasing by a certain step. Let's say 1 millivolt. Each step, the pulse increases by 1 millivolt. Let us say, it could be 1 millivolt, could be 10 millivolt. That is as per the design. So, coming here, it finds coming here in this line, it finds that the signal blue dotted line is still more than the last signal, so it takes one step more higher, right? The output here, output of the sample and hold circuit goes up by one defined step. Then it has got a certain width. Step cannot be infinitely small, right? So coming to the next step here, it finds that the signal value, blue line, is less than the earlier step. So it takes one step down. Then coming here, it finds that signal value is larger than the last step. So it takes one step higher. So naturally, when the signal is approximately continuously fixed value, or the signal value is within one step, say our step size is 1 millivolt, then if the signal variation is within 1 millivolt, then it will go keep on going up and down, and like that. Then it finds the signal is going up, takes step higher, another step higher, until so. If you look at this, now look at this schematic diagram. This is a sample and hold circuit which creates these steps of signal. Now, if it is goes high, then there is a circuit which creates a 1. If it is low, it creates a 0. Now, this 1 or low, up if 1 and down, and 0 if down, it goes to a up-down counter. It is a digital circuit. That means suppose it it continuously there are 3 steps of 1. So it will be 1, then 2, then 3, like that. Or it will be down, then 1 plus 2, and then again 1, and then maybe again 0, and then again minus 1. It's a up-down counter. This counter value goes to analog converter. So this counter remembers last sample height. Now counter remembers the last sample height, and last sample height is converted into an analog value, and it is given to the comparator. So what this comparator does, comparator always compares between the present sample value and the last step height. And then again it finds out whether it is more or less. If the present signal is more, it takes one step higher. If it takes one step higher, it creates a 0. One signal 1 here, binary bit 1 here, right? Here we have shown how the delta t is varying. See, from here your delta t is positive, one step, here another step, here again one step, here again one step, here again one step. So from here to here, the output is one step. Coming here, the output becomes 0 because it is one step down. So it becomes 0. So anyway, this is delta t, output of this comparator, right? Output of the comparator is only giving 1 or 0. If it gives 1, that means go one step higher. If it gives 0, that it indicates that go one step down. Now, it's described here, what I just told you, it is described here. If the present value mt, the first value of m dash t, then the accumulator raises m dash t only by a fixed amount s. A step. This step is your design. You want to make it 1 volt or 10 millivolt, it's your design. If mt is lower than the past value, then the accumulator lowers m dash t by 1 step. So it is only creating 1 step high or 1 step low. Now here you must have already guessed that if the signal variation is very fast, that means signal is going high very fast or going low very fast. If you have that kind of a signal, you have to first study the signal. Like a doctor, he first studies the patient, then he prescribes the medicine. As an engineer also must first study the signal properly, all its aspects, and then prescribe the circuit or the schematic, right? So here, what I was going to tell you, you have already observed if the signal variation is very fast, then there can be problem. there can be problem. Like here, the signal is going up, 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 and the steps are also going one step higher, one step higher, one step higher. But suppose now this output can go up by one single step, not more than that. And that step may be 1 millivolt. But if your signal rises by 3 millivolt, then what happens? Then there will be a situation like this. Your signal, your output will never be up with the signal, and obviously there will be an error, right? So we go to that and hence starting the coder needs a clock cycles to catch up with the signal, because signal always starts with zero. Sorry, our system always starts with zero, but signal did not always start with zero. Signal may start with some 5 millivolt, 6 millivolt, any value. So at the first few clock cycles, it will take some few steps to catch up with the signal. And that's not a problem in practical application. Now, if the signal continues to rise or fall slowly, then m dash t, that means output, it follows it. Like here, it follows it, right? Although there is a step error, right? But it follows it. If the signal is steady, then what happens here? There is a kind of plus minus error continues, and that error is called noise, right? That error is called granular noise. And if the signal rises very fast, faster than the slope that you have designed, what is the slope that you have designed? Your x-axis is time and y-axis is some millivolt signal value. And say y-axis, one step is S for step. And say that S is 1 millivolt. And say each time step is 1 millisecond. Then what is the slope you are allowing? 1 millivolt parts millisecond. If the signal rises faster than that or falls faster than that, then you will have problem. And that problem is called slope overload error. So there are two types of possible errors. One is a granular noise if the signal keeps on steady for a long time, and there is a slope overload error. Now, slope overload error can be eliminated or reduced, or possibility can be reduced by detailed observation of the signal variation nature, and your design value of sampling rate and your design value of step, right? Now, what do you do to slope overload error? Yours now your slope is y-axis is S, that is step value, some millivolt, and x-axis is T or TB. I have taken it at TS, that means the time for each sample. So your design slope is S by TS maximum. Now, if the S should be higher, if you want to make S by TS higher, then you have two options. Either you make S higher, that means you make step higher. If you make step larger, then again you increase the quantization error. You could make TS smaller. That means you take samples more repeatedly. If you take TS smaller, suppose instead of 1 millisecond, you take TS as 0.5 millisecond, then you have to send your digital data at twice the rate, double the rate. If you send your digital data at double the rate, then your bandwidth requirement becomes double, right? Suppose earlier you were sending your data at 1 Mbps. Now, if you want to send your data at 2 Mbps, of course, channel bandwidth requirement doubles. So there is a there is a problem in both way. If you increase S, then quantization error increases. If you decrease TS, then bandwidth requirement increases. Anyway, so what it appears primarily that if the signal variation is not very fast, and if the signal nature is what I should say is if it can be assumed, or if it can be if it is known, the nature of signal variation, if it is known, then you can always use this linear delta modulation, where bit rate is very, very small, because instead of sending 8 bits, you are sending only 1 bit. So obviously bandwidth requirement is 1 by 8. So this is the basic scheme of linear delta modulation. Then we shall see one aspect that sometimes you get this question in your exams, that uh, whether delta modulation is good for speech coding. That means somebody is giving a lecture or classroom lecture, whether delta modulation is good or not. So the description here, it's not very difficult. See, normal speech bandwidth is 3.5 kilohertz. Possibly you know already. When we speak, our uh, highest frequency is 3.5 kilohertz, not more than that. Not more than that. For men, it is even lower. For women, it's little higher. But in average, it is 3.5 kilohertz. Bandwidth is 3.5 kilohertz. What is the Nyquist rate? 7 kilohertz, double of the bandwidth, right? So in speech coding, a 7 kilohertz sampling rate is good in digital electronics. So standard sampling frequency in speech 8 kilohertz. And this is a standard, circuit becomes easier. Also, it provides a guard band. Now, let me tell you what is a guard band. Now, see, uh, if sample it at 7 kilohertz, 7 kilohertz is needed, but we do it at 8 kilohertz. That means for each sample train, data train, we allow 8 kilohertz band. Signal is 7 kilohertz. So at the end of each sideband, there is a 1 kilohertz gap unused. There is no signal. And that is good for electronics. That is good for electronics because you will be always sending or transmitting multiple channels. So each channel at a different carrier frequency. If you keep a gap of 8 kilohertz from one carrier to another carrier, then from one sideband to another sideband, there will be always a 1 kilohertz gap, unused gap. That is a little wastage of bandwidth, channel bandwidth, but it provides a guard band. That means it reduces any chance of one channel overlapping with another channel and creating crosstalk. This is provides a guard band. So anyway, speech is normally sampled at 8 kilohertz. And speech is normally coded for 8-bit coding. Whether it is essentially necessary or not, it is normally done on 8-bit because you have to have a global standard. If you do it at 3-bit, somebody else does that at 5-bit, then when you try to receive somebody else's signal, you'll have a problem. So it has become a global standard that speech signal is coded by 8-bit, right? And 8-bit coding at 8 kilohertz rate. That means at you are sending signal at the rate of 8,000 per second, 8 kilohertz. and each symbol has 8 bits. So what is the bit rate? Is 8 kilo multiplied by 8. That is 64 kilohertz is your bit rate, right? So standard bit rate for pulse code modulation is 64 kilohertz. Pulse code modulation is the basic technique that we discussed 2 3 days back. So remember that in pulse code modulation, uh, standard or conventional bit rate is 84 kilohertz and sample rate is bit rate is 64 kilohertz and sample rate is 8 kilohertz. Now, let us compare this information with delta modulation. Then we have to avoid overload error that we discussed slide. It has been communication engineers by repeated trial and error that if your delta modulation electronics can handle a 800 hertz sinusoidal signal of same amplitude. 800 hertz sinusoidal signal is a simple sine signal, so you have very little or very easy mathematics here, right? If you have a complex signal, then mathematics becomes problem. Found that if your system can handle 800 hertz sinusoid without any overload error, then your electronics will be able to have standard speeches. Somebody giving lecture, somebody giving classroom lecture, somebody talking. Some standard speech signal can be handled without any overload error. Now, what is the maximum slope of a 800 hertz signal? A sinusoid, its maximum slope is when it is at 0, right? So, this sinusoid is signified by A, capital A is the amplitude, A sine 2 pi ft. So, we differentiate with respect to time and we find out its value at t equal to 0. A sine 2 pi ft differentiation is A multiplied by 2 pi f into cos 2 pi ft, and when we find its value at 0, cos 2 pi ft when t equal to 0 is 1, so it is a 2 pi f. So slope of 800 hertz slope of a sinusoid signal of frequency f, maximum slope at 0 is a 2 pi f, where a is the peak value. Now, order to avoid slope overload error, our design slope of the system, that means I show you system, our slope is y-axis is s and x-axis is time ts. So s by ts is the slope, right? My design system slope s by must be more than a 2 pi f. And 1 by ts is fs, that's sampling frequency. So SFS must be more than A 2 pi f. So Fs must be more than pi f into 2a by s. It's 2a by s. 2a is peak to peak amplitude. And s is the step. And in 8-bit coding, 2 to the power 8 is 256. So number of steps. So 2a by s is actually number of steps in the whole range. So in 8-bit coding, 2 to the power 8 is 256. So total number of steps is 256. So Fs should be more than pi into F is 800 hertz. Already we know F is 800 hertz. There is one extra F here that we shall remove. So it is pi into 800 into 256. So pi into 800 into 256 is 640 kilohertz. That means sampling frequency than 640 kilohertz. And what is our PCM sampling frequency? Is only 8 kilohertz. Right? So standard pulse code modulation sampling frequency is 8 kilohertz, whereas I have 640 kilohertz. So what I need is 80 times higher sampling rate. That means the same speech, if I could use standard pulse code modulation, the basic system, and instead of that, if I try to use the delta modulation, I need 80 times higher sampling rate. 80 times higher sampling rate is too much. Too much. Electronics will be very costly. There will be 80 times higher pulse bit rate in the channel, 80 times higher channel bandwidth is required. And that is why final conclusion is, hence, delta modulation is not advised to encode speech. You can use delta modulation for some other application, but not for speech, right? Here we used delta modulation. Next, we have adaptive delta modulation, that is another advanced method of delta modulation. We shall see this in our next lecture. Okay.